The summer morning brought clear skies over Hampshire as a large commer lorry turned off the main road and approached the guarded entrance of the Royal Aircraft establishment at Farnborough. The facility, nestled in the rolling countryside south of London, had served as Britain's premier aviation research centre since before the Great War. And in the summer of 1940, it had become one of the nation's most critical military installations. Behind the lorry's canvas covering sat an extraordinary cargo, a Messerschmitt Bf 109E fighter, the Luftwaffe's primary single-seat fighter, recovered from a field in Kent, where it had crash-landed 3 days earlier, following a dogfight over the English Channel. The aircraft represented one of the most complete examples of Germany's frontline fighter yet captured, and its arrival at Farnborough had been anticipated with considerable interest by the technical staff, responsible for evaluating enemy equipment. The lorry proceeded slowly along the facility's internal roads, passing administrative buildings, wind tunnel complexes, and various workshops before reaching a large hangar on the establishment's eastern perimeter. Here, a team of engineers and technicians had assembled to receive the German fighter and begin what promised to be an intensive examination of its design, construction, and operational characteristics. The hangar doors stood open, revealing a cavernous interior where several other captured aircraft sat in various stages of disassembly, each surrounded by tools, measuring equipment, and documentation detailing their analysis. The morning air carried the distinctive smell of aviation fuel, engine oil, and the metallic scent of aluminum, creating an atmosphere that was simultaneously industrial and scientific. Leading the reception team was Geoffrey Wickham, a senior aeronautical engineer whose career at Farnborough stretched back to the early 1930s. At 48 years old, Wickham represented a generation of British aviation pioneers who had witnessed the transformation of aircraft from wood and fabric biplanes to sophisticated all-metal monoplanes capable of speeds exceeding 300 miles per hour. His background included work on various RAF fighter programs, and he had personally contributed to the development of several key technologies that now equipped British combat aircraft. Beside him stood Squadron Leader Peter Harrington, an RAF liaison officer who had flown Spitfires operationally during the early weeks of the Battle of Britain before being reassigned to technical evaluation duties following a minor injury. Harrington's practical combat experience would prove valuable in assessing the captured aircraft from a tactical perspective, complementing the engineer's technical analysis. Also present were several junior engineers, technicians from the establishment's workshops, and a photographer whose task would be to document every stage of the examination process. The group watched as the lorry backed carefully into the hangar, its driver following hand signals from ground crew who guided the vehicle to the designated examination area. When the lorry stopped, several men moved quickly to secure the load and begin unloading procedures. The canvas covering was pulled back, revealing the Messerschmitt in daylight for the first time since its recovery. The aircraft sat on a specially constructed transport cradle, its damaged landing gear having been replaced by temporary supports. The fighter's overall condition was remarkably good, considering its forced landing. The fuselage remained largely intact, the wings showed only minor damage, and the engine, though silent, appeared complete. The aircraft's camouflage scheme of mottled grey and green upper surfaces, with light blue undersides, was typical of Luftwaffe fighters operating over the Channel, and the yellow nose marking identified it as belonging to one of the units based in the Pas-de-Calais region of occupied France. As the Messerschmitt was carefully lowered from the lorry and positioned on the hangar floor using a mobile crane, Wickham conducted his first close examination of the aircraft. Even before any systematic analysis began, certain characteristics immediately caught his attention. The fighter was noticeably smaller than he had expected, more compact than a Spitfire or Hurricane, with a lean, purposeful appearance that spoke to careful attention to aerodynamic efficiency. The fuselage was narrow, barely wide enough to accommodate a pilot, and the overall design emphasized minimalism and weight reduction. The aircraft measured approximately 9 meters in length, with a wingspan of just under 10 meters, dimensions that suggested priorities different from those driving British fighter design. The canopy, partially damaged during the crash landing, featured a distinctive framework of metal bracing, that provided structural strength while compromising visibility compared to the cleaner canopy designs of British fighters. The propeller, a three-bladed variable pitch unit, showed sophisticated manufacturing with carefully shaped blades designed for optimal efficiency. Most strikingly, the aircraft's construction featured flush-riveted metal skinning and remarkably clean aerodynamic lines, with minimal protrusions or irregularities to disturb airflow. Everything about the Messerschmitt's external appearance suggested an aircraft designed with obsessive attention to drag reduction and performance optimization. Squadron Leader Harrington approached the aircraft from the pilot's perspective, examining the cockpit layout and noting features that would be operationally significant. The sideways opening canopy provided good access, but created vulnerability during emergency egress. The armored windscreen and pilot protection suggested German awareness of combat realities. The control stick's positioning and the rudder pedal arrangement appeared conventional, indicating that transitioning to the type would not require radical changes in piloting technique. As morning progressed toward midday and the hangar filled with the sounds of activity, the team prepared to begin their detailed examination of what many were already recognizing as a formidable opponent worthy of serious respect. The afternoon brought the first systematic documentation phase as the photographer methodically recorded the Messerschmitt from every angle while engineers took measurements and made preliminary sketches. Wickham had organized the evaluation into several phases: external examination and documentation, systems analysis, engine removal and study, component disassembly, and finally a comprehensive report synthesizing findings and recommendations. The process would take weeks, possibly months, depending on what they discovered and how deeply they needed to investigate particular systems. For now, the focus remained on external characteristics and overall impressions before more invasive examination began. Junior engineers moved around the aircraft with tape measures and calipers, recording dimensions and creating detailed drawings that would allow accurate comparison with British fighters. The wing's airfoil profile received particular attention, with careful measurements taken at multiple stations along the span to document the section shape and thickness ratio. British aerodynamicists had developed considerable expertise in airfoil design, and understanding the profile used on the Messerschmitt would provide insights into German thinking about optimal lift-to-drag characteristics and performance priorities. The tail surfaces similarly underwent careful measurement, with engineers noting the relatively small size of the horizontal stabilizer and elevator compared to British practice. This suggested either superior aerodynamic efficiency or different assumptions about control authority requirements. The landing gear, though damaged, revealed interesting design details. The main gear retracted outward into the wings rather than inward toward the fuselage centerline, a choice that created a wider track for ground handling, but complicated the retraction mechanism and potentially created structural challenges. Everything observed during this initial examination would be documented, analyzed, and compared against British fighter designs to identify areas where German engineers had made different technical choices and to understand the reasoning behind those decisions. As evening approached and natural light faded, powerful electric lamps were positioned around the Messerschmitt, creating harsh shadows that emphasized every rivet line and panel joint. The hangar had taken on the atmosphere of a laboratory, where a precious specimen awaited dissection and analysis. Wickham gathered his team for a preliminary discussion, sharing initial observations and planning the next phase of work. The consensus was already forming that this German fighter represented sophisticated engineering, though the full extent of its capabilities and the details of its design philosophy remained to be discovered. Squadron Leader Harrington contributed observations from his combat experience, noting that the Messerschmitt's performance in actual combat, its speed, climb rate, and maneuverability suggested an aircraft optimized for different tactical priorities than British fighters. Where Spitfires and Hurricanes emphasized turning performance and gun platform stability, the Messerschmitt appeared designed for energy tactics, using speed and climb rate to control engagement timing and geometry. These operational characteristics must flow from specific design choices and engineering priorities that the detailed examination would hopefully reveal. As the team departed for the evening, leaving the captured fighter under guard in the now quiet hangar, there was a shared sense of anticipation about what the coming days would reveal. The Messerschmitt sat silent under the electric lights, a machine that had crossed the Channel to fight in the skies over England and had now become an object of intense study, its secrets soon to be exposed to the engineers, whose task was to understand everything about their adversaries' most important fighter aircraft. The following morning brought renewed activity as the technical team assembled to begin detailed external examination of the Messerschmitt's construction methods and manufacturing quality. The summer weather remained clear, though the hangar's interior stayed relatively cool, protected from the direct sun by thick walls and high ceilings, designed to moderate temperature fluctuations that might affect sensitive instruments and equipment. Wickham had prepared a structured examination protocol overnight, identifying specific areas requiring detailed analysis and assigning team members to focus on particular systems or components. The first priority was understanding how the aircraft was built, the materials used, the joining methods employed, the manufacturing techniques evident in the finished product, and the overall construction philosophy that guided German engineers. British aircraft construction had evolved considerably over the previous decade, transitioning from mixed wood and metal structures to all-metal stressed skin designs that offered superior strength-to-weight ratios and better aerodynamic efficiency. The Messerschmitt clearly represented a fully modern all-metal aircraft, but the specific techniques and approaches used in its construction might differ significantly from British practice, potentially revealing alternative solutions to common engineering challenges. Several engineers positioned themselves around different sections of the fighter, equipped with magnifying glasses, calipers, thickness gauges, and notebooks for recording observations. The fuselage became the first focus of detailed study, with particular attention to how the metal skin was attached to the underlying structure and what type of internal framework supported the external covering. What immediately impressed the examining engineers was the quality of the surface finish and the sophistication of the manufacturing techniques evident throughout the aircraft. The fuselage skin consisted of flush-riveted aluminum alloy panels, carefully formed to create smooth aerodynamic contours with minimal irregularities. The riveting quality was exceptional. Each rivet head sat precisely flush with the surrounding metal, creating a continuous surface that would minimize drag and turbulent airflow. British aircraft manufacturers had adopted flush riveting for critical areas, but often used protruding rivets in less aerodynamically sensitive regions to simplify manufacturing and reduce costs. The Messerschmitt appeared to use flush riveting almost universally, suggesting either different cost-benefit calculations or more advanced manufacturing capabilities that made the technique economically feasible across the entire airframe. The panel joints showed careful attention to alignment and fit, with minimal gaps or mismatches that might create aerodynamic disturbances. This level of finish required either highly skilled labor or sophisticated tooling and jigs that ensured consistent results regardless of individual worker variation. One engineer, carefully examining a fuselage joint with magnifying equipment, noted that the German manufacturing tolerances appeared tighter than typical British practice. Though this might reflect differences between prototype or early production techniques versus the mass production methods that British factories were now employing to build fighters in unprecedented quantities. The fuselage's internal structure, visible through inspection panels and the damaged sections, revealed a sophisticated framework of formers and stringers, creating a semi-monocoque construction where both the skin and the underlying framework contributed to structural strength. This approach was familiar to British engineers. Modern all-metal aircraft universally employed similar principles, but the execution, details and the specific solutions to structural challenges showed distinctive German approaches. The wing construction commanded particular attention due to its direct impact on aerodynamic performance and its role in determining the aircraft's flight characteristics. British engineers carefully examined the wing's attachment to the fuselage, the internal spar structure, visible through access panels, and the skin's forming and attachment methods. The Messerschmitt's wing featured a relatively thin profile, with a smooth, carefully maintained surface contour that suggested attention to laminar flow principles. British aerodynamicists understood that maintaining smooth, undisturbed airflow over a wing's surface could significantly reduce drag, but achieving this in practice required extraordinary manufacturing precision to maintain the designed contour without irregularities that would trigger turbulent flow. The German wing showed evidence of such precision. Its surface was remarkably fair, with minimal waviness or distortion. The skin panels were formed with obvious care, and their attachment to the underlying structure avoided creating bumps or depressions that would compromise the aerodynamic surface. The leading-edge construction was particularly interesting, featuring a carefully shaped profile that would influence stall characteristics and maximum lift generation. British fighters like the Spitfire employed different leading-edge designs, and comparing the approaches would provide insights into different priorities regarding handling qualities and performance characteristics. The wing's trailing edge, where the control surfaces attached, showed sophisticated hinge arrangements and control linkages that would allow detailed analysis of the control system design. Everything about the wing's construction spoke to careful engineering and meticulous manufacturing, suggesting that German aircraft production combined advanced design with high-quality execution, at least for this frontline fighter type. The control surfaces, ailerons, elevator, and rudder received detailed examination as their design directly influenced the aircraft's handling qualities and combat maneuverability. The ailerons were relatively small compared to British fighter practice, suggesting either different philosophies regarding roll rate priorities or superior aerodynamic efficiency that achieved adequate control authority with smaller surfaces. The hinge mechanisms were beautifully engineered, featuring carefully manufactured bearings and linkages that would provide smooth, low-friction movement. British engineers noted that the control surface construction used fabric covering over metal frameworks, a choice that contrasted with the increasingly common British practice of using all-metal control surfaces. The fabric covering was lighter and potentially allowed some aerodynamic flexibility that might improve control characteristics, but it was also more vulnerable to weather deterioration and battle damage. The German choice suggested different priority weighting between these competing factors. The control cables and linkages visible through access panels showed careful routing and substantial engineering attention to mechanical advantage, friction reduction, and reliability. The elevator trim tab mechanism was particularly sophisticated, featuring a cockpit adjustable system that would allow pilots to trim the aircraft for hands-off flight at different speeds and power settings. This attention to pilot workload reduction and aircraft refinement suggested a mature design that had undergone considerable development and testing before entering operational service. Squadron Leader Harrington, examining these systems from a pilot's perspective, noted that such refinement would contribute to combat effectiveness by reducing pilot fatigue and allowing greater attention to tactical situation awareness rather than constant wrestling with aircraft control. As the morning examination progressed, the team's respect for German engineering continued growing. The Messerschmitt was not simply a functional fighter hastily designed to meet urgent military requirements. It was a carefully developed aircraft showing evidence of sophisticated engineering, extensive testing, and refined manufacturing. Every system examined revealed thoughtful design choices and quality execution. The landing gear mechanism, despite its damaged condition, showed ingenious engineering in the retraction linkages that folded the main gear outward into the wings. The complexity of this mechanism was considerable, with multiple pivots, locks, and actuating systems required to achieve the desired kinematics, yet the execution appeared reliable and well sorted. British engineers photographed and sketched the mechanism extensively, recognizing that understanding this approach might inform their own landing gear design efforts. The engine mounting system, visible with the engine cowling panels removed, featured a robust structure that would support the power plant's weight and absorb operational loads while allowing the engine to be removed relatively easily for maintenance. The cowling panels themselves were beautifully formed aluminum pieces, carefully shaped to create smooth airflow around the engine while providing access for inspection and service. Everything examined during this second day of analysis reinforced the emerging picture. The Messerschmitt Bf 109E was an aircraft representing the best of German aeronautical engineering, built to high standards and designed with clear performance priorities that differed in interesting ways from British fighter philosophy. The implications of these findings would become even more significant as the team moved toward examining the aircraft's most interesting system, its engine and the fuel injection technology that enabled performance, characteristics British fighters could not match. The third day of examination brought the team to what many considered the most critical aspect of their analysis, the Messerschmitt's power plant and its associated systems. The Daimler-Benz DB601A engine that powered the Bf 109E represented the culmination of German liquid-cooled aero engine development, and British intelligence had long been interested in understanding its capabilities and the technologies that enabled its performance. Wickham had arranged for additional specialists to join the examination for this phase, engineers from Rolls-Royce, who brought expertise in high-performance engine design, and technical officers from the RAF's operational commands, who understood the tactical implications of engine performance characteristics. The morning began with careful removal of the remaining engine cowling panels and accessories, exposing the complete power plant for detailed examination. The DB601A was an inverted V12 configuration, meaning the cylinders were arranged in a V with the point facing downward, allowing the propeller shaft to sit relatively low and providing good forward visibility over the engine. This layout was familiar to British engineers. Rolls-Royce had used similar configurations, but the specific implementation and the technologies incorporated into the German engine would prove revolutionary. The engine displaced approximately 33.9 litres and produced around 1,100 horsepower at takeoff power, performance comparable to the Rolls-Royce Merlin engines powering Spitfires and Hurricanes. What differed was not the basic power output, but rather the systems and technologies that achieved that performance and the operational characteristics that resulted from the design choices. As engineers began detailed examination of the engine's external components and systems, one feature immediately commanded attention: the fuel delivery system. Unlike British engines, which used carburetors to mix fuel and air before delivery to the cylinders, the Daimler-Benz engine employed direct fuel injection, with fuel being sprayed directly into each cylinder under pressure. This seemingly simple difference had profound implications for aircraft performance and combat tactics. The Rolls-Royce engineers present immediately recognized the significance, as their own company had experimented with fuel injection, but had not yet implemented it in production engines due to development challenges and manufacturing complexity. The German implementation appeared mature and well-developed, suggesting considerable engineering effort had been invested in perfecting the system. The fuel injection pump, mounted on the engine and driven by the crankshaft, was a beautifully machined piece of precision engineering. Its task was to deliver precisely metered amounts of fuel to each cylinder at exactly the right moment in the combustion cycle, maintaining proper mixture ratios across all operating conditions, from idle to maximum power. The complexity of achieving this reliably was substantial, requiring extraordinarily tight manufacturing tolerances and sophisticated mechanical design. British engineers photographed and sketched the pump extensively, noting every detail of its construction, operating principles, and integration with the engine's other systems. The implications of fuel injection began to crystallize as the technical team discussed the system's advantages. In a conventional carburetor system, fuel was mixed with air in the carburetor body before being delivered to the cylinders through intake manifolds. This approach worked well under most conditions, but it had a critical limitation. During negative G maneuvers, when an aircraft pushed over into a dive or performed inverted flight, the fuel in the carburetor's float chamber would become disrupted by the negative acceleration, causing fuel starvation and engine power loss or complete stoppage. Squadron leader Harrington immediately grasped the tactical significance of this limitation and its impact on combat operations. British fighter pilots had learned through bitter experience that if a Messerschmitt attacked from above and they attempted to evade by pushing forward into a dive, Their own engines would cut out momentarily due to carburetor fuel starvation, while the pursuing German fighter, with its fuel injection system unaffected by negative G-forces, could maintain full power throughout the maneuver. This gave Messerschmitt pilots a crucial advantage in certain combat situations, allowing them to pursue diving targets without the power interruption that affected British fighters. RAF pilots had developed tactics to work around this limitation, executing a half roll before diving to maintain positive G forces, or using other maneuvers that avoided prolonged negative G conditions. But these workarounds were imperfect and added complexity to already demanding combat situations. The captured engine's fuel injection system explained a performance characteristic that operational pilots had observed but not fully understood, and its discovery would have immediate implications for both tactical doctrine and future British engine development programs. The Rolls-Royce engineers, examining the injection system in detail, recognized that British engine manufacturers needed to accelerate their own fuel injection development efforts to match this capability. The technology was not unknown. Rolls-Royce had experimented with it, but seeing a mature, operational implementation in an enemy engine that was being mass-produced and deployed throughout the Luftwaffe fighter force made clear that this was not merely an experimental technology but a practical system that conferred real combat advantages. Discussions immediately began about how quickly British engines might be retrofitted or redesigned to incorporate similar capabilities, though the engineers recognized that developing, testing, and manufacturing fuel injection systems at scale would require considerable time and resources. The examination continued with detailed analysis of other engine systems and components. The supercharger, which compressed intake air to maintain power output at altitude, featured a sophisticated design with careful attention to aerodynamic efficiency and mechanical reliability. The cooling system, using liquid coolant circulating through passages in the engine block and cylinder heads, showed refined engineering with efficient heat exchange and minimal weight. The engine's construction quality was exceptional throughout, with precisely machined components, careful assembly, and attention to detail that spoke to both excellent design and high manufacturing standards. British engineers noted that while British engine makers certainly produced quality power plants, the German engine showed a level of refinement and sophisticated engineering that commanded respect. The propeller control system, which automatically adjusted blade pitch to maintain optimal efficiency across different flight conditions, represented another area of advanced development. The constant speed propeller mechanism featured complex hydraulic and mechanical systems that required precise manufacturing and careful integration with engine controls. British aircraft used similar technology. Constant speed propellers had become standard on modern fighters, but examining the German implementation provided insights into alternative approaches to common engineering challenges and potentially revealed solutions that British designers might adapt. As the day progressed and more details emerged from the engine examination, the technical team recognized they were studying not just a single component, but a complete power plant system representing years of development effort, sophisticated engineering, and mature manufacturing capabilities. The implications extended beyond simply understanding how the Messerschmitt's engine worked. This examination was revealing the depth of German aeronautical engineering expertise and the level of technological sophistication that British industry would need to match and exceed to maintain competitive advantage in future aircraft development. The afternoon brought discussions about how to preserve and test the captured engine. Simply understanding its construction was valuable, but actually running the engine under controlled conditions would provide even more insights into its performance characteristics, operating envelope, and any limitations or weaknesses that might be exploitable. The decision was made to attempt starting the engine after completing the current examination phase, assuming no damage was discovered that would prevent safe operation. This would require fuel system repairs, coolant system checks, and various other preparations, but the potential knowledge gained would justify the effort. British engineers could measure actual power output, fuel consumption, thermal characteristics, and operational behavior across different conditions. This data would inform not only immediate tactical understanding, but also longer-term aircraft and engine development programs. As evening approached and the team concluded the day's work, Wickham prepared notes for an interim report to senior RAF leadership and Air Ministry officials. The fuel injection system discovery alone was significant enough to warrant immediate communication, as it explained observed combat characteristics and had direct implications for pilot tactics and future engine development. The report would emphasize that the Messerschmitt represented sophisticated engineering, backed by mature manufacturing capabilities, that certain German technological approaches, particularly fuel injection, conferred real combat advantages, and that British industry needed to respond with accelerated development of comparable or superior technologies. The captured engine was revealing truths that were simultaneously impressive and concerning, forcing British engineers to acknowledge that their German counterparts possessed considerable expertise and that technological competition would be as important as numerical production in determining air superiority. The following days brought continued examination as the team systematically explored every aspect of the Messerschmitt's design, construction, and systems integration. With the engine study complete and the fuel injection system's significance fully appreciated, attention turned to understanding the broader design philosophy that guided the aircraft's development and the priorities that shaped engineering decisions throughout the project. Wickham organized a series of discussions where the team would analyze not individual components, but rather the relationships between systems, the compromises inherent in any design, and the underlying assumptions about operational requirements that influenced German engineers' choices. These discussions took place in a conference room adjacent to the hangar, where the team could reference their detailed notes, photographs, and measurements while stepping back from the immediate technical minutiae to consider larger patterns and principles. Squadron Leader Harrington participated fully in these discussions, contributing the operational pilot's perspective that would help translate engineering characteristics into combat implications. The consensus emerging from these analytical sessions was that the Messerschmitt represented a design optimized for energy tactics and vertical combat, prioritizing speed climb rate and dive performance over sustained turning ability or low-speed handling qualities. This contrasted with British fighters, particularly the Spitfire, which emphasized excellent turning performance and remained controllable and effective across a wide speed range, including the relatively low speeds characteristic of turning dogfights. The German aircraft appeared designed for a different kind of combat, using superior speed and climb rate to control engagement timing, attacking from advantageous positions, and disengaging by diving away when circumstances became unfavorable. This tactical philosophy was evident in numerous specific design choices throughout the aircraft. The relatively small wing area gave the Messerschmitt high wing loading, the ratio of weight to wing area, which meant higher speeds were required for level flight, but also resulted in better high-speed performance and reduced drag. Aircraft with high wing loading typically had higher top speeds and better dive characteristics, but turned more slowly and required higher landing speeds. Low wing loading provided opposite characteristics, better turning but slower maximum speeds. The Germans had clearly prioritized speed over turning ability, accepting the trade-off because their tactical doctrine emphasized different combat techniques. The control surface's relatively small size reinforced this priority, adequate for high-speed maneuvers but potentially limiting control authority at the lower speeds characteristic of sustained turning combat. British fighters, with their larger control surfaces and different wing designs, could outturn the Messerschmitt in most circumstances, but if German pilots avoided turning combat and instead used speed and altitude advantages to dictate engagement terms, the Messerschmitt's design priorities would be validated. Squadron Leader Harrington confirmed that combat experience supported this analysis. Messerschmitt pilots typically attacked from altitude, made high-speed passes, and broke away by diving when pressed, using their aircraft's strengths rather than accepting combat in situations where British fighters' characteristics would be advantageous. Understanding this design philosophy was as valuable as understanding individual technical systems because it revealed the tactical doctrine guiding Luftwaffe fighter operations and suggested how RAF tactics might be optimized to exploit British fighters' relative advantages while minimizing exposure to German strengths. The examination of the aircraft's armament installation and ammunition capacity provided additional insights into German operational priorities. The Bf-109E's standard armament consisted of 4 guns, 2 rifle-caliber machine guns in the upper forward fuselage firing through the propeller arc, and 2 20mm cannon mounted in the wings. This combination provided both volume of fire from the machine guns and destructive power from the cannon, creating a weapons package that was lethal against bomber and fighter targets alike. The ammunition capacity, however, was relatively limited. The cannon carried only 60 rounds per gun, providing approximately 7 seconds of firing time. British fighters typically carried more ammunition, allowing longer engagements or multiple attack runs, though their weapons were generally lighter caliber. The German choice suggested combat doctrine, emphasizing accurate, decisive attacks rather than extended firing passes. A pilot who could position precisely and fire accurately could destroy targets with short bursts, making limited ammunition less constraining. This approach demanded high pilot skill and excellent training, qualities the Luftwaffe apparently assumed their pilots would possess. The gun installation also revealed sophisticated engineering in the synchronization gear that allowed the fuselage-mounted machine guns to fire through the spinning propeller without striking the blades. This technology was familiar. Synchronization gear had existed since the First World War, but the German implementation was refined and reliable, indicating mature development. The wing-mounted cannon installation showed careful attention to mounting rigidity and recoil management, as the substantial forces generated during cannon firing could affect aircraft handling, if not properly controlled. Everything about the armament installation spoke to thoughtful integration of weapons with the airframe, ensuring that firepower could be delivered effectively without compromising flight. Characteristics: the cockpit layout and pilot interface design received careful examination, as these factors directly influenced combat effectiveness through their impact on pilot workload, situational awareness, and decision-making capability. The Messerschmitt's cockpit was compact and relatively Spartan compared to British fighters, with instruments arranged functionally but without excessive space or comfort considerations. The side-opening canopy provided reasonable access but created potential emergency egress challenges compared to sliding canopy designs. Visibility, while adequate, was not exceptional. The canopy framework created blind spots, and the view to the rear was partially obstructed by fuselage structure and the pilot's headrest armor. British fighters, particularly later Spitfire variants with improved canopy designs, offered superior visibility, a factor that would prove increasingly important as combat experience emphasized the critical importance of seeing the enemy first. The control layout appeared logical and well organized, with frequently used controls positioned for easy reach and critical instruments prominently located in the pilot's scan pattern. The Germans had clearly invested effort in optimizing the human-machine interface within the constraints of the aircraft's compact dimensions. The oxygen system, essential for high-altitude operations, featured a simple but effective design. The radio installation, while examined only in limited detail due to security restrictions on electronics intelligence, appeared to be standard Luftwaffe equipment, providing air-to-air and air-to-ground communication capability. Overall, the cockpit reflected a design philosophy that prioritized functionality over comfort, accepting cramped conditions and limited visibility as acceptable trade-offs for the aircraft's aerodynamic efficiency and performance characteristics. As the examination entered its second week, the team began synthesizing their findings into a coherent understanding of what the Messerschmitt represented and what it revealed about German aviation capabilities. The aircraft was clearly the product of a mature, sophisticated design and development process backed by advanced manufacturing capabilities and a clear understanding of combat requirements. Its engineering was excellent, not perfect, with some areas where British approaches might be superior, but certainly representing world-class aeronautical development. The design priorities differed from British fighters in interesting ways, suggesting different tactical doctrines and different assumptions about what characteristics most contributed to combat effectiveness. The fuel injection system represented a significant technological advantage that British engines needed to match. The overall construction quality and attention to detail suggested German industry was capable of producing military equipment to high standards, even while engaged in large-scale war production. This final point was perhaps the most strategically significant finding. The Messerschmitt was not a crude, hastily built wartime expedient, but rather a refined, well-manufactured aircraft that Germany was apparently producing in substantial quantities. Britain faced an adversary with serious aeronautical engineering expertise and substantial industrial capability, making the air war a contest between roughly equal technological capabilities, where victory would be determined by factors beyond simple engineering superiority: pilot training, tactical doctrine, production capacity, and strategic employment of available forces. As Wickham drafted sections of the formal evaluation report, he recognized that these findings would influence British fighter development for years to come, validating some existing programs while suggesting areas requiring increased emphasis or new research directions.